Okay, now we're starting the recording. We went over heterolytic and homolytic cleavages. At least I remembered. Imagine if I didn't remember, I would cry. So, yeah, homolytic and heterolytic cleavage. Maybe if you guys want to go into the book and look at the actual definitions, that could be beneficial because he could ask, like when the fill in the blank vocab questions, this could be one of them. But for 6.2, 6.3, there was a lot of stuff in the book about math calculations and stuff like that. I don't think any of that would show up on the exam from what I've seen, and I've like been doing this for a while, so I haven't seen anything where he's actually asking to do math calculations. But most likely what he's gonna ask is maybe to identify like the transition state, reactants, products, and if there's like an intermediate, if it's like a two-step reaction, then he might have you label those types of things. Something that we look at in kinetics, when we're looking at like kinetics versus thermodynamics, in kinetics, we're looking at the activation energy. And then we have that something like a catalyst can lower the activation energy, which is why it will speed up the reaction. So then 6.5 is talking about the rate of reactions. So it's kind of just, you have your K constant times your reactants, and then that varies based on what type of reaction. So if we have like Sn1 or Sn2, then the rates are going to be different. And then that's pretty much, I'm kind of just giving you guys tidbits from questions that I think he would ask, or like things that I've seen before. So is that cool with you guys? Hopefully it's helping a little bit. Okay, cool. So here in 6.6, we have kinetics is talking about the rate of reactions, thermodynamics is talking about the equilibrium. So again, if he were to have you guys, maybe he would give you guys this energy diagram and then be like, which one is the thermodynamic product and which one is the kinetic product? And we can kind of see that because kinetic, that's talking about like the speed of the reaction. So if we see a lower activation energy, it's going to happen faster. But we can see that this is the thermodynamic product because it's more stable and the activation energy is larger. But maybe if it had something like this, where the activation energy is the same, and then it was like that, then that would still be the thermodynamic product, and it would also be the kinetic product. Because we have more stable and the activation energy is like that. Cool?
Cool.
Awesome. So then moving on, we have 6.7. Okay, this is just like a bunch of definitions. We have nucleophiles are electron-rich. They have an electron-rich center, which is generally negative or partial negative. So I saw this S thing, and a lot of people were calling it S in the group chat, or not in the group chat, like in the class. Maybe because there's no like emoticon for it or anything, but this just means like partial negative. And then an example for that is, I think this is oxide, where you can see that there's like a lone pair that's able to be donated. Whereas over here we have an electrophile, which just means that it has an electron deficient center, which is generally positively charged or partial positive. And then you can have something like this, where we have an actual carbocation, or we have something where there's a partial positive. And this was kind of seen in the worksheet today, where we had that bromine. And then I'll talk about something in a second, and you'll see why this would be, why it's important to actually like identify the molecules. And it really will help you understand how these reactions are happening. Because honestly, if you understand the things on this page, then it's really going to help you drawing the arrows, seeing the reaction mechanisms. It's going to make sense. So yeah, I just used the word carbocation and carbanion. So carbanion is just a negatively charged carbon, and then this is what it would look like. And something to note is that this would happen if we had a carbon, like if we're actually drawing out what this carbon looks like, it has a hydrogen like this and then a lone pair on it. So then the charge is -1. It wouldn't happen if our carbon was like this. It wouldn't have 5 bonds to have that negative, because if you ever see a carbon, most likely it's not going to have 5 bonds because carbon is just not happy that way. So that's just a little, in case something comes up on the exam and it's like, oh, which one is the most likely to form a carbon ion, or yeah, a carbon ion, and then there's a carbon with 5 bonds, it would I guess if it were, you guys were choosing between 5 bonds and the one that actually just has like a lone pair on it, it would be the lone pair. Cool?
Yeah. Cool.
Hopefully that made sense. And then we have our carbocation, which is just a positively charged carbon. And that, again, comes into play when we're looking at our reactions. 6.8, we have something negative attacks something positive. So this is really what we see in every single reaction. So we'll see like a nucleophile attacking an electrophile, or maybe, oh, I forgot some example here, but I was thinking of doing something like this, where there's like a double bond, and then like an OH like this, and then the double bond would come, actually, it wouldn't do that. It would do maybe something like this. Let's see, we have a water. So then this double bond is going to come and attack the hydrogen. And then we'll have a product that looks like this, where we have our hydrogen from before and then new hydrogen. And then that's the old hydrogen. So again, we know that bonds in general are just made up of electrons like this. So let's say that we have something in like, so this is the p orbital. This is what's making our pi bond, is p orbitals overlapping. So yeah, that's kind of like exam 1 material. But yeah, I repeat this like all the time, but negative goes to positive. So we'll have like electrons going and attacking a carbon ion, or sorry, a carbocation. Yeah, my bad. Just like that. That's what we'll see in almost pretty much like all the reactions. Speaking of reactions, these 4 things that I have written over here are what like all reactions are made up of. So over here, the first thing that we can have is a nucleophilic attack, which is just when we have a nucleophile attacking an electrophile. So in this case, we have a chlorine with a negative charge attacking this carbocation. And then this was what our product would look like. Again, we have negative going to positive. Then over here, we have a loss of leaving group. This is different than negative going to positive, because this is just, technically in this case, the carbon in the center looks like this, but it's able to leave because these other carbons are giving their electrons to that center, like that. So then it's not super unhappy forming this, because they're kind of like sharing their electrons like that. But the chlorine is like, I'm so fed up of being in this environment where all of your friends are just giving you attention, and then he just leaves. That is hyperconjugation, right? I believe that is what it was called in the book, but no, in the book it was called loss of leaving group.
Yeah.
In the book it was called loss of leaving group. Hyperconjugation, let me think. Yeah, hyperconjugation is like when those electrons are being donated. So there's like an unequal sharing of electrons, but those other carbons are kind of just sacrificing. Sorry, I was like trying to think of what that even is. But yeah, that is what would happen in order for chlorine to leave. So then the next thing that we would have is proton transfer. And we know that protons are just hydrogen. So over here we have something like an OH, and then the lone pair on the oxygen is going to go and grab that hydrogen, and then we're going to be left with like 2 water molecules. And we know that OH is a bad leaving group, and I have them listed later about like ranking their leaving group abilities. But OH is like a super bad leaving group, wouldn't leave on its own. So over here we can do something where we add another hydrogen on there so that it becomes a water molecule, and then that leaves a little bit easier, but it's still not considered like a good leaving group or like a best leaving group. So yeah, that is an example of a reaction. That's kind of something that you see a lot in Orgo 2 during reactions in order to make OH leave. And then we have rearrangements, and we see this in Who wants to tell me what kind of reactions?
For the rearrangements, are you talking about like if it's gonna be like substitution or elimination or like Sn1 or E1 or something like that?
Yeah, is it going to happen in like Sn1, Sn2, E1, or E2? Where would we see rearrangement?
That would happen in like
And the
Sn1,
E's.
but I forgot about the E's. Cause I thought like for the
Well,
S ones, you like have like nucleophilic attack and then like a leaving group.
it wouldn't be in either SNs because you're
Yeah, I didn't see it in Sn1. Is that in the book? Because I did not.
no, because you're just doing like the nucleophilic attack. There wouldn't really be like a need for the hydride shift, but when you're making the double bond, that's when you would need hydride
Exactly.
shift. Which one would it be, E1 or E2, or is it for both?
So I have it in this chart here. Let me get rid of the stuff that I did during office hours. I have it just in E1 reaction. So if you guys actually want to take a little screenshot of this, this is a pretty helpful chart of just like Sn1, Sn2, E1, E2, just like the basics of it. Cool. Okay. I'll let you guys take those pictures. And then let's go back to this. Yeah, so we're going to see this in E1 reactions. And they can be called 1,2 hydride shifts or just hydride shifts. And you can see that because it's just moving from like 1 to 2. It kind of just depends on, I think your book was just calling it hydride shifts, but I think when I learned it as 1, 2. So just in case you guys see that on the exam. And yeah, this creates anything we'll see in mechanisms or reactions. So then 6.11, we have, okay, yeah, so this is another example of just a hydride shift. And it's important to remember that the carbocation isn't going to rearrange into something where it's going to be less stable. You always want your carbocation to be more stable. And even though these are generally just intermediates, it might be important depending on the type of reagent that we have. So let's say that we have like, and we were talking about this in office hours again, where let's say that we have like in Sn1, we're gonna want it to be a little bit more substituted. Okay, so it says, in the book, there are rearrangements for Sn1 reactions. Okay, cool. If it says that there are rearrangements for Sn1, let's go ahead and go up here and then say, also watch out for rearrangements. Rearrangements. Cool. Are you going to send these notes in the group me? I will. I'm going to try and finish writing out the book, and then things where I see like, oh, this is a really great place to ask a question, or like where Dr. Dowdy would like most likely ask a question, or like I've seen him ask questions before. Yeah, so I'll send that in there. And then I have like these like important to know kind of things. So he can ask a question like, which of the following molecules will not undergo carbocation rearrangement? So then we'll see things where something like this would not undergo carbocation rearrangement, because either way, if it's moving to the right or left, it's still going to be have that 2-degree substitution. So it's like, why would I even move? You know what I mean?
Just to clarify, the tertiary is more stable than like a secondary, for example, right?
Okay. And yeah, so we have for carbocations, tertiary is more stable, and then secondary, and then primary is the least stable.
Okay, so it's only gonna shift if it goes from like 1 to 2 or 2 to 3. Okay.
Exactly. And I'll try and do a practice problem like that in a sec, or like once we're done going over these notes. So over here, it was saying stuff about allylic carbons and that's kind of just like a definition thing again. Maybe he would ask like circle a carbon in a structure and then be like, oh, what type of carbon is this? But I've never really seen him do that before. I'm not really sure why. When I wrote this, I was like, oh, this seems similar to beta carbons, and then we have like alpha carbons, but it's actually different than that. That is a separate topic. So this is just what an allylic carbon is, in case you guys were curious. Then next thing we have, this is an interesting mechanism to see. You can see that I like really simplified these notes. I was kind of writing them like I would write them for myself if I hadn't like seen these things before. So I have like R just means like a carbon chain. If you guys didn't know that, don't feel bad. Yeah, I was just putting that there. And then over here we can see electrons being pushed. So I just wanted to include this in case something like this shows up on the exam, that it's not the first time that you're seeing it. Even though this is like a little bit more of an advanced topic, you will see this in like the mechanisms that we're going to do in the next couple chapters. But yeah, this is just what electron pushing looks like. And again, we see this negative going to positive, because if we were to look at this again, oxygen is more electronegative, which means that even though it's not like a super big partial negative, it has like a little bit of a partial negative compared to the carbon. Cool.
Yep.
Awesome.
Yes.
Awesome. So then over here, I know you guys are probably like, oh yeah, I just got done with learning all the pKa values, where Neda was like, yeah, memorize those pKa values. I wouldn't memorize them again, but just it's important to note that in a lot of these reactions, I'm trying really hard not to say, oh, we saw this in office hours, because it's probably really annoying at this point. But a lot of these reactions are going to move towards stability, which is why we generally don't see endothermic reactions. And just for reference, this is what an endothermic reaction is, where there's more energy at the end of it compared to something where we have an exothermic reaction, where we have less energy at the end of it. This is really what all mechanisms are trying to, or reactions are moving towards. So we know that something will actually occur if the pKa is larger at the end of it.
So wait,
So that's just,
if the pKa is larger, sorry, I got a bit confused. Does that make it exothermic, or am I connecting like the wrong dots together?
it's kind of like that, yeah. But it's not necessarily related, like pKa isn't directly related to being exothermic and endothermic, is it?
I don't know.
I feel like there's that equation where it's like pKa, and then we have equals like A over B over, or times C and D, and then that equals like something that you use in your like delta H formula thing. But he's not going to ask you math questions, but we just know that reactions want to move towards stability. So reactions want to be exothermic a lot of the time from what we're seeing. So it's kind of just what I was trying to say.
Oh, okay.
Mm-hmm. So then that was the end of chapter 6. The other stuff in there, definitely read over it, but I was just seeing things where I was like, oh, he would definitely ask a question on this. That's not to say that he won't ask questions on other things.
Yep.
So over here in chapter 7, we were talking about alkyl halides, nucleophilic substitution, and elimination reactions. So the chapter kind of just starts off as talking about what happens in substitution and elimination reactions. Substitution, the nucleophile replaces the halogen, which is Cl, bromine, and iodine. We don't really see fluorine here, for the reason that fluorine is really electronegative. It says it specifically in the book why we don't see fluorine. Let me check really quick so I can tell you guys the exact reason. And if somebody knows it, then you can put it in chat so that I'm not having to look. Is it size? That doesn't sound like what it said in the book. It could be why, but I just want to make sure. It says it a little bit later in the chapter. I know that, and you have like iodine. When it has those ions, it has like bromine, chlorine, and iodine as ions somewhere in chapter 7. And then it says something about fluorine. And if I command F for fluorine, it would probably bring up 300,000 things. So I'm not going to do that. Okay, that will be your homework for after, because you know what? Something like that I can definitely see popping up on the exam. It's like, why is fluorine not a halogen that reacts in substitution reactions? Again, it's a little bit simple.
I thought it was
obviously,
like, I know people are saying it is with size, but I thought it was also because like combined with size and like chlorine is so electronegative, and I know like it was saying iodide is like the best at it because it is bigger, but it also like isn't as electronegative, so it has like better stability of all of its electrons or something like that. Yeah, like polarity, polarizable.
Yeah, I think I remember it saying stuff more so about polarity compared to the size of the element. But yeah, so let's say polarity for now, but definitely don't just trust me on that. I don't think that Dr. Daddy would ask questions like that because he doesn't really ask just like basic concept questions like that. He more so, especially because you guys only have like what, I think 25 questions. He's not really going to want to waste one on like, oh, why is fluorine not one of the halogens? He'll probably ask something a little bit more difficult, like rank the following and increasing reactivity. And then you would have like fluorine, chlorine, bromine, and iodine. It would be more so an application question in that case. It talks about the shell that is formed around fluorine because it's not good at being polarizable. Fluorine, it is much more difficult to react with partial positive charge. Okay, there you go. That is why. So it's a polarity thing, which is why fluorine is not considered one of the halogens that can usually replace it. So then we have, that's what substitution looks like. And then for elimination, we have a pi bond formed at the end of it. And then usually we're reacting with some sort of base. So page 272 has a picture of your electrostatic maps, and you might see something like that on the exam. And then you might be asked like, oh, where is the electron rich part of it, and which one is the, or like which one is the electron poor? I've definitely seen questions where he's just asking about electrostatic maps, and that sometimes throws people off because that's not really something that you're just looking at. So definitely just take a second to try and understand and see where like red just means that it's electron rich. So it's pretty much as simple as that. But when you look at it, it's kind of one of those questions where you're like, oh, now I definitely know that I know how to answer this. What is this thing? Oh my goodness, did you see that? That is so cool.
Nope.
It's very, very nice. Okay, so over here, this is leaving group ability. You can kind of understand what's happening here. Iodine is larger than bromine, which is larger than chlorine, which is why iodine is a better leaving group than the other two. He could most definitely ask a question saying rank in order of increasing leaving group ability. I don't know, there's like something in my gut telling me that he's going to ask you a question like that. So just take a little second, look at these, know that NH2 is like the worst leaving group ever. It's so funny. in Orgo 2, a lot of reactions happen with NH2, and you have to do like so many things to it to even like kick it off of the reaction. So yes, that is just its ability to leave a reaction. Cool. Very nice.
Oh, sorry.
Yeah, what's up?
Oh, for like the middle part with like when there's water and that ring with sulfur, what makes them like good leaving groups? Because I understand like that halogen pattern so far, but I'm confused like in that little sandwich.
I'm gonna be honest, I have never seen this thing over here as a leaving group. Actually, I probably have, but I don't remember seeing it as a leaving group right now.
I think that's in like the very end. Isn't there like a specific name for that, like with a T or something? What is that?
Oh yeah, I know what you're talking about.
Yeah, it's like, oh god, I can't find it.
They like touched on it at the end of the chapter.
Yeah, it was like really.
That and alcohols.
It was right before alcohols.
You guys go over alcohols in this chapter?
Yeah.
They like barely touched on it at the very end.
It's like.
Are you guys referring to tert-butyl?
No, there's. Oh wait, I have it. Tosylate.
Tosylate. There you go. And it's like, what is it like shortens it into something
like ROTS.
POS or OTS. There you go.
Rot.
That is definitely an Orgo 2 concept. But definitely just like kind of be familiar with it right now. Just know that it would be a leaving group.
Yeah, the Kinetics did substitution and elimination reactions with methylates, tosylates, and triflates.
Knowing Dr. Dowdy, he's probably not going to do something like include tosylate and ask you guys for increasing. Most likely he's going to have NH2, OH, and then maybe like chlorine or iodine in there. So he usually keeps it pretty simple, but just in case he does ask something a little bit harder, just be familiar with the other ones. And it's really not like that hard to look at, but yeah, this is just like something where, again, it's a question where you wouldn't necessarily be like, why would he, like, oh, I don't actually have to look at that chart. So yeah. And then again, it just randomly starts talking about nomenclature of things that you guys have like already talked about, like, oh, like when chlorine is on there, and how do you name that? So if you are unfamiliar with nomenclature, just do a couple practice problems. I feel like that's the best thing to do. And that's like kind of the best way to prepare for nomenclature questions. So here we are with Sn2 reactions. The kinetics, we have both the alkyl halide and the nucleophile are both being included. You could definitely ask a question like, have an Sn2 reaction mechanism with like something that it would react with. So let's say like Sn2 react with a protosolvent. Let's say that we have like, let's just make it like a secondary one like this, and what would come off of it? I'm not really sure. Let's have like iodine over, or what would, how do they happen? The nucleophile replaces, okay, yeah. So let's have like iodine over here, and then a protic solvent, we're looking at them, and then we have something like acetone. Pretty, huh? So then the rate would look like this. We're talking about the rate? I don't even remember at this point.
I think so.
And
talking about kinetics.
yeah, so this is what the rate would look like for this reaction. Does that make sense?
Yeah.
Okay, awesome.
Wait, quick question. How would you involve the solvent, the rate? I thought it was a nucleophile. Would acetone be a good nucleophile? Would you use like a halide or other things? Because I thought acetone was a bad nucleophile because it like lacks a negative charge.
So in the book, it mentions nucleophiles and also it mentions strong nucleophiles as being important for Sn2 reactions, but I'm like, oh my gosh, my computer's gonna die. I'm like 99% sure that when I took the class, the book would just talk about aprotic and protic solvents, which is what Dr. Dowdy has really been including in those worksheets. And those worksheets are a really good, just like determiner of what kind of questions he asks. I feel like he asks pretty similar questions on the exam. You guys feel the same way?
Yeah, sometimes with that, or like I know some people said like skill builders or like Orion, like he would ask like specific questions from those.
Yeah, when I was in the class, he would ask literally just questions from the book, which is why I would do every single question problem. Because after I found that out, I was like, and that's the thing, is that there are a lot of things in organic chemistry that people don't tell you, like tricks that they know. Like, oh, do all the practice problems, because he asks questions from there. And then you just keep it to themselves. So I'm trying to help you guys out a little bit. And yes. So somebody said Sn2 and E2 are aprotic, Sn1 and E1 are protic. Let me scroll up and see what I have here. Sn1 I have as protic. What did I just put in this reaction? Did I have an Sn?
If it's protic, would it be Sn1? Or
No, you put aprotic.
I did put an aprotic solvent. That is correct. I'm sorry, you guys. This should be a protic solvent for an Sn2 reaction. Although that reaction would happen, because technically this is secondary.
Wait, but if it's Sn2, you would want aprotic, right?
If it is Sn2, then we want aprotic, yes. My bad, you guys.
Wait, so
Cool.
does that apply to like E1 and E2 as well? Like the protic and aprotic solvent?
Let me see where I have the notes up there about E1 and E2. E1, I have that, yeah. E1 is protic and then E2 is aprotic. But
Okay.
I also, more specifically for E1, and I feel like these are the types of reactions I would see for E1 and E2. E1 really reacts with weak nucleophiles or weak bases, whereas E2 will react with base only.
would E2 also react with like bulky bases too?
And E2 reacts with, do both of them react with bulky bases? It just depends on the substitution, or let me think. Bulky bases only react with like the ends of it, the end hydrogens.
Yeah, the only thing bulky bases would do is like affect if your major product is like some like your rich product is off. But like I know that Sn1 and Sn2 like they cannot work with like the 3 bulky bases.
Mm-hmm. Yeah, so something like tert-butyl or tert-butoxide, that wouldn't react with like Sn1 or Sn2. It just, they both react with bulky bases. It just depends on which product is going to be the major product or the minor product. Cool.
Wait, could you repeat that, please?
So E1 and E2 both react with bulky bases. It would just determine which one is going to be your major product and which one is going to be your minor product. That's the only difference between the two.
Okay. Thank you.
Yeah, so these are a list of the strong nucleophiles, weak nucleophiles, protic solvents, and aprotic solvents. What chart where you guys talk, a lot of you guys are talking about a chart in the book where
Yeah, I know what
like
you're talking about. I brought it up
what
as a question.
what page is that on?
It's in 7.11.
Figure 7.19, I think.
What?
I was saying
I
it's
think-
figure 7.19 in
yeah.
the book.
I think it's 7.8 is the section, I think. I'm not sure.
No, I just went in
No,
it.
it's definitely 7.11.
Yeah. It's the one about, it tells you like with primary, secondary, tertiary, and then it tells you like whether it's going to be E2, E1, all of that. It's like really colorful.
Yeah, I think that table is only for like if you have competitions. Like for instance, for like tertiary, there's a competition between like Sn2 and E2 if you have like a strong base and a strong nucleophile. And so they're just like telling you which one is going to be like your major product between like an E2 and a.
The reason why a lot of people were asking about it is because it's just like kind of inconsistent with what Dr. Dadu was talking about, because it says like a secondary weak base or secondary substrate that's reacting with a weak base or weak nucleophile like won't happen. But Dr. Dadu's been doing problems like with that situation and it does happen. So he didn't really kind of like understand what we were asking, but basically I think like we should just do what he's saying so it will go through. Yeah, that's
this is the one that you guys are looking at. What was he saying about the strong bases?
No, I was asking about the weak base, weak nucleophile. You see how it has like an X? It's basically saying like the reaction won't even occur. So I asked him about that and he said that it would.
Probably didn't understand, honestly.
Well, he had like examples on his PowerPoint. That's why I asked in the first.
Really?
How would that reaction occur though? Because if you're producing like a carbocation that's like primary, that would be like super unstable.
Well, he didn't do it for primary. It was mostly for secondary, because for secondary and when it's weak nucleophile or weak base, it's going to be either Sn1 or E1. It's the same thing for tertiary, but like in the book, it says secondary doesn't happen, but he was saying it'll be Sn1 or E1.
And this is using a lot of my brain cells trying to think about this.
I would just say like based on his PowerPoints, like if it's secondary and it's a weak base or weak nucleophile, follow the same thing as tertiary. Like it's either going to be Sn1 or E1 because that's what he was saying. He's saying
Methyl shift or hydride shift, can you technically have like a secondary substrate? You just still like do Sn1 or E1 reaction. That makes sense.
Yeah, what I'm imagining happening is that you're turning the carbocation, even though the original thing that you may be working with is secondary, maybe doing like a shift to make it tertiary so that it would be able to go through with this Sn1 E1.
Yeah, because even in the book, they have an example of that where like you have a secondary substrate, but like if you do a methyl shift after you like have that first step, then it still could go under like an Sn1 or E1 reaction. And I think we had a question on the worksheet. I don't know if it was a worksheet, but he had a problem where we did a methyl shift on like a secondary carbocation.
Yeah, definitely look into methyl shift because those are fun and important. We're almost done with what I have here. Yeah, it was 7.11. Let me share my screen again. Thinking. Okay, I'm sharing my screen. Start broadcasting. Okay, let's go back to notability. Yep, so this is just like a list of strong nucleophiles, weak nucleophiles, protic solvents, aprotic solvents. And these are the notes. I will try and finish taking these notes. It's probably going to end up being like 5 pages or something like that. considering that my physics homework did get the due date was moved to tomorrow. So I can definitely do that for you guys today. But now moving on to this, I'm going to think about how I'm going to do this. Is the chapter 7 PowerPoint locked, you guys?
I just tried to go on it and it says access denied. You don't have access to view this. And that's where I was going to go to reference his example of it.
Somebody sent in the chat. Thank you so much.
Thank you.
Thinking. Everything I'm doing today is requiring a lot of thinking. It's pretty upsetting to me, actually. Okay, let's see what questions this would line up with for me. Would this be, are any of these from this chapter that I have right here? I don't think that they would be. Did I do an exam 1 review for you guys?
I think it was just an exam 2 review.
Damn, I suck. I should have done that for you guys because I had so much exam 1 stuff. My bad. Maybe for the final.
I guess.
Yes. Okay. Oh my gosh, fun. Are you guys ready to rumble?
And tumble. Let's go.
Yes, let's go. Okay, so over here, let's go ahead and I'm gonna unfortunately have to write the questions out, which I know is really, since my handwriting is not really that great all of the time, but hopefully you guys will be able to read it. So let's go ahead and say which of the following energy diagrams represents the course of an exothermic Sn1 reaction. Okay, so over here in the first one, we have something that looks like this. Okay, go off. Second one, we have something that looks like this. Okay, that's looking pretty exothermic to me. What do you guys think?
Looking pretty
Yes.
stable than products.
I mean, it is exothermic. Over here, we have this. Interesting. That looks pretty tempting. And then we have this last one here. So let's go ahead and break down each one of these. And obviously, we have energy on the Y and reaction coordinate here. So what does this look like? First of all, is it going to be Sn1 or Sn2?
Sn1?
Yep, this is going to be Sn1, but is this endothermic or exothermic?
Endothermic.
Yep, this is going to be endothermic. So then over here, we have one step. So what is that going to look like?
Sn2?
Yep, this is Sn2. It's also exothermic though, but we're looking for an Sn1 reaction. This one, what does this look like?
Sn1?
Yep. Oh, you said Sn1. Yeah, that is Sn1. And this, spoiler alert, it's also exothermic. And then just for good measure, this last one here is going to be Sn2 and endothermic. So based off of this, our answer is going to be this. Does that make sense?
Yeah, that wasn't too bad.
Yep, exactly. That's what I'm saying. You just gotta keep a nice positive attitude while you're doing this. Positive attitude will get you far in organic chemistry. What is the order of rate from fastest to slowest for the following reaction? Oh, wow, this is going to be a fun one. I'm not sure if this is related to your material right now. I feel like it is, though. So we have, what is the order of rates from fastest to slowest? So we have bromine and a nucleophile. And then we have the nucleophile. So what kind of reaction is this? Elimination or substitution?
Substitution.
Yep, this is going to be a substitution reaction. And then these are our options. So we have nucleophile, and then we have 1 CH3OH, 2 CH3O, and 3 CH3NH2. So I personally like to go in and write out what each of these looks like, just so I can see what I'm actually working with. And we have an OH like that. 2 looks like this, where we have a CH3, and then an O with all of those nice electrons on there. Okay, and then 3. So we have CH3 NH2 with a lone pair like that. So something to note is that strong nucleophiles are strong electron donors. Oxygen, like that, which is number 2, is the best because it has the lone pairs, the most lone pairs, and is negatively charged. NH2 is the second, which is 3, is the second best because the pKa is around 35. But even if you didn't know that, we know that NH2, what kind of base is that?
That would be a weak base.
It would be a stronger base, right? Because it's a conjugate base of a very weak acid.
Yeah, so compared to OH, which one would be a stronger base, NH2 or OH?
OH.
It would be NH2 is a stronger base.
Yeah, NH2 is going to be the stronger base. I'm trying to think of how to explain that. Really, pKa values. If you're going to memorize any 2 pKa values for this exam, I would say memorizing NH2 and OH would be the best. But honestly, at this point, you don't have to memorize them because I'm telling you that NH2 is just a better base. So in case something like this does come up, we have OH is the worst because we have the pKa of it is around 18. So then we have fastest to slowest. That's another thing that Dr. Gowdy does sometimes. I think I had this question one time and I flipped it. So I ended up putting 132. Base strength increases from right to left on the periodic table. Okay, yeah, so, oh, that is a question.
Yeah, so basically I was watching a YouTube video and like looking at your periodic table, like
you have fluorine, oxygen, nitrogen, and carbon. So like it was saying that your base strength is going to increase as you go like from the right to the left. So like nitrogen is on the left compared to oxygen, so it would be a stronger base. That makes sense.
Okay. Does that make sense for everybody else? There's a trend for bases, but I feel like that could be a little bit difficult just if there was something where it was like NH2 compared to, or I guess actually that's a really good thing too. So just look at the trend if you are unsure. But I'm sure that none of you guys are going to be unsure because you guys are all so smart. So yes, this is another question. Do I have any questions on this one?
Should I just use the trend then? Because I thought that OH would be a better base than the nitrogen.
Yeah, I think they just never talk about NH2 in our book, really. They always talk about like OH being such a good base. So, because like I guess if you turn it into an acid, it's like a weak acid.
Yeah, that's what I was thinking.
Yeah, so I guess that's why it was like confusing.
Yes, well, this is just clarification in case Dr. Dowdy asks something like this on the exam. Then you guys just know now that NH2 is a stronger base than OH. Cool.
Okay.
Perfect. Okay, so next thing that we have here, rank the following. Indicated bonds in order of decreasing bond dissociation energy. And before you guys freak out and you're like, oh my God, I have to memorize the bond dissociation energies. No, I have a life hack for you guys. So the first thing, CCl3, this is the bond we're looking at, and this is going to be number 1, number 2. And again, we're looking at that same bond over there. Then we have ICCl3, 3. And then we have Cl, CCl3. And we're looking at that bond, and this is going to be 4. So let's go ahead and look at one of our trends. So we have increasing size. We go from fluorine, smaller than chlorine, which is smaller than bromine, which is smaller than iodine. Then note, smaller the atom, more energy you need to break the bond. Which makes sense because let's say that we have something like this. Let's say this is fluorine, and we have our protons in here, and they're like super, super positive, super cute. And then we have our electrons right here for fluorine. Let's say that we have like a negative charge on it. Then these electrons it's much easier for these electrons to like go towards these protons here than it is for something, say, iodine, where we have a couple of shells between there. So these protons over here are able to be subdued. Obviously, this is not like an accurate representation since the first one, it does have 2 electrons only. So yeah, just drawing these in, which is so extra of me. I'm so annoying. Anyways, these electrons are able to like kind of go towards the positive. So then this one can be like, oh, look, now we're on this bond right here. So it's just able to be broken easier because it's not as close to the nucleus, if that makes sense. So then the alternative to this one is that the larger the molecule, the less energy you need to break the bond. So let me go ahead and get rid of this drawing right here. With this information, what do you guys think that the answer is going to be?
Would it be fluorine? And then I'm trying to look at it. Fluorine is like the first one,
Mhm.
the smallest. And then after fluorine would be chlorine. I'm trying to think of it.
Is that 4? Okay, cool.
And then bromine and iodine.
Bromine. And then iodine. Perfect. So the answer would be 2, 4, 1, 3. Because we're talking about decreasing bond dissociation energy. So this would mean this is the most and this is the least amount of energy needed to break the bond. Does that make sense for everybody?
Yeah, that's actually pretty simple.
Mm-hmm.
And no math.
Yep, no math. Okay, next question. Let's do which of the following steps could be found on in, this should be in an Sn1 mechanism. So I'm gonna trip you guys up a little bit and give you guys a chair confirmation. And this is something where, since we haven't really looked at them recently, well, I guess like you guys saw them like 3 weeks ago or something like that, but that's kind of a long time ago at this point. I don't want you guys to be like, oh my gosh, can't believe this is on the exam. Who knows? It could be. So just in case, familiarizing yourself with these, you have a plus on this, hydrogen, 3. Let's say the hydrogen is moving there. And then the last one looks like this, which is 4. Let's say that we have a hydrogen here. And let's say that there's a bromine with a minus charge that goes to grab this hydrogen and then forms a bond there. So in this first one right here, there really isn't a reaction happening. So that's not really a step that would be found in an Sn1 mechanism. So not this one. Then over here, oh, okay, we have a nucleophile attacking an electrophile. That seems pretty tempting. What do you guys think about that?
Yeah.
Like
Tempted.
understand.
Okay, yeah, tempting answer. So let's go ahead and just say, let's put a check mark next to that for right now. Over here, we have this hydrogen moving towards there. There really isn't even anything grabbing the hydrogen. Seems kind of shady to me, but what does this kind of look like? Let's say that we had a bromine over here grabbing this hydrogen. Then what does that kind of look like to us?
Elimination.
Yeah, this would look like an elimination reaction. So I'm gonna write elim right there. And then looking at 4, that's like straight up, again, we're looking at the same thing as 3 elimination reactions. So based off of knowing the fact that 3 and 4 are elimination reactions, first one doesn't even look like anything is really happening, then we know that this is going to be the answer.
How do those
I have like a quick question.
Mm-hmm. Yeah, what's up?
So with like number 2, like right? So like the bromine, I know he was like talking about something about like how if it can't go in like an axial position or something like that. Like I was just a little confused with how that would
What did
play
he say?
into this.
I think he was talking about
So
stability, right?
yeah, it was like something about like how like bromine on like an axial position isn't stable or something like that.
Okay, so bromine
Or
here is on an axial position. So then it wouldn't be able to react, or it would react.
He said it would be.
like it would react. Yeah, it would react, but like for like number 2, for example, like because you're showing like the bromine on that carbocation like reacting with that, and so wouldn't that then become like an axial, and wouldn't that be like not stable?
Well, no, because the methyls in the equatorial.
Yeah, the methyls are need more priority in the equatorial than the bromine.
Okay, there you go. We have an explanation that the methyl in axial has more priority than the bromine.
I know what they're talking about, because when we're doing like elimination, you have to have it in like anti-periplanar position. So like for instance, you have to have whatever your leaving group is in the axial, and whatever hydrogen you're taking also has to be in the same, like they both have to be axial to each other. So like he was talking about how like your more stable one is what you're gonna find the like the cyclohexane in more. I'm sorry for the music in the background.
Sounds like you're in a nightclub.
No, I'm not
I've
lineage.
personally never been to a nightclub, but it does sound like what a nightclub would sound like.
No, it's just lineage. So I'm sorry.
I'm actually like, I found the PowerPoint thing that they're talking about is talking about
Okay.
planar geometry, and yeah, so it's just saying that what, okay, it says there's like a chlorine and an H, and the H is axial, the chlorine is equatorial, and it says that that's more stable than a chlorine and an axial and a hydrogen. I don't know, that's so confusing.
So
Well,
would that only apply to like what's it called for elimination?
Oh,
where
okay,
like
I get it now. Yeah. So yeah, what you're saying is like if like our if like Br was attached where that methyl is on number 2 in equatorial, it wouldn't react because it's already stable. But if it's in a axial position, it would. I think.
Yeah, that's right.
Asking.
But it's not really about the stability. I thought it's like the thing with like having to be anti-periplanar, and like it's only anti-periplanar if both are axial to each other.
That's what it says on the.
You're thinking of for elimination reactions when there's only
yeah,
one
right.
proton
You're right.
in the B
My fault,
position. Yeah, this is just talking about
You're
the
right, you're
stability of
The cyclohexane.
cyclohexane, like
Or the
which
chair.
one will react. Yeah. So
Gotcha,
basically,
gotcha.
the
Yeah, that makes sense.
axial is the only one that's gonna react.
Yeah. So.
Yeah, I get what you guys mean. It makes sense.
I have a question.
Yeah, what's up? Honestly, if I'm being 100% honest, I don't really, all I know is that equatorial is more stable than axial position, and that's about it. And I feel like there were no arrows even. I'm sure there's an explanation to why one is not the answer. I'm for some reason my head is not clicking as to why it is. But yeah, so what is your question?
Oh, like how is 3 and 4 eliminations? Because I thought 4 was gonna be Sn2 for the problem that you wrote.
You're forming a pi bond, like straight up forming a pi bond. So when will the recording be posted? Hopefully like right after the meeting. Yes, I'm going to put up a question for you guys right now, and then you guys can do the question. I'll let you guys like talk it over with one another. So this one is just going to be rank leaving groups worst to least. Sorry, you guys. worst to least leaving group. 1, where let's say 1 is NH2, 2 is H2O. This one isn't going to be too bad since we literally just went over this. I gave you guys a cheat sheet.
Best.
Okay, I'll let you guys talk this over.
But just to clarify, are we doing worst to least or worst to best?
I think worst to best.
You literally wrote worst to least.
That's fine.
Oh my!
I thought there was some concept I missed.
There you go. Worst to best.
So NH2 is the worst.
Right.
Would the next one be water?
I have
No, OH would be the. Yeah, OH is second. It shows a better leaving group than OH. So it'd be like 1, 3, then 2, and then 4.
1,
So
3,
what-
2, then 4.
1, 3, 2, 4.
Yeah, I think.
Yeah, because carbon,
That's right.
the methyl group with the negative charge would be the best because it has a negative charge.
Why are you guys saying that that methyl group is going to be the best?
That's what I'm confused on.
I feel like it's the negative charge.
So you guys just feel like the methyl group is going to be the best one. It's a feeling you guys are having. A group feeling that this methyl group is the best leaving group. That methyl, even over water, is going to be
No. Yeah, all right, guys. All right, 4 is not the best. Let's move forward to the second worst. It is not the best.
Did we get the first parts right? NH2 is the worst.
I just know H2O is gonna be better than OH, but that methyl is throwing me off right now.
I don't think
Wait, is methyl the worst?
like
Dang it. All right.
In our chart that we wrote down, it says NH2 is the worst.
But I know CH wouldn't be really good at like being polarizable because it can't really distribute that negative charge well. But then it does have a negative charge, which the others don't.
I'm going to give you guys a hint and tell you that NH2 is the second worst.
Okay.
Right. So methyl is the worst.
Right.
Okay, so then what do you guys think the new ranking is going to be?
4, 1, 3, 2.
Yes, that is so beautiful. I'm so proud of you guys.
Just took a little bit.
The answer is going to be 4, 1, 3, 2.
Wait, is it because that C8 or that C is so bad at like having that negative charge?
Let's go over why. So NH2, it's less electronegative. The best way to think about this really is electronegativity. So we have less electronegative than oxygen. So we see oxygen here and also oxygen there, but it's more electronegative, more electro than carbon. Carbon is the least electronegative. And therefore, the worst leaving group. OH, very electronegative compared to the other ones, but H2O over here is the most electronegative. It's the most stable on its own, and then therefore it is going to be the best leaving group. I think the best way to look at this is looking at the stability of it on its own. On its own, CH3 with a negative charge would probably like explode or something. I'm not really sure what would happen to it, but you really just, I don't think that you see methyls with negative charges in nature. So therefore, 4 is the worst leaving group. Then we have NH2. NH2 will survive, probably try and pick up a hydrogen to become NH3 so that it gets rid of that negative charge. But CH3 will probably just like immediately go and latch onto another molecule that has a carbocation. So then we have 1, and then OH is the second best, but H2O is the most stable on its own. What are you more likely to see in nature? A water molecule where it's so happy and content with its existence, or an oxygen where, or an OH where it's like, oh, I'm an acid, I'm gonna go and like attack someone, literally.
Water molecule.
Yeah, the water molecule is definitely gonna be more stable. So yeah, that's pretty much my explanation. I hope you guys enjoyed that.
So basically, you just look for on its own, like which one is the least like stable, I guess you're saying.
Yeah,
That's how
you
rank
look for
them?
which one, how stable it is on its own.
Okay.
But also, if you still aren't able to kind of decide that way, then look at electronegativity is always a really good thing to do. Okay, so this next one, so fun. I think we did this, something like this in class today. So we're gonna do rank the following alkyl halides in order of increasing rates in Sn2 reactions with NaCN. I'm going to mention it, but I did this in office hours today. So here we have Br. Here we have Cl. That's going to be 2. I'm actually going to write them as 1 and 2. Not Roman numerals. I'm not a fan of Roman numerals, honestly. I feel like, okay, I barely even know how to do the question. No, you're asking me to use Roman numerals. The best thing that we can do here is, let's just state some of our facts. So we know that Sn2 prefers primary and secondary. The tertiary barely reacts, and most of the time it like really won't react at all. And then leaving group and accessibility most important. So if we're looking at this one here, this carbon is going to be primary, this carbon is secondary, and that's not even like that's a methyl. This one is tertiary. This is another tertiary, and this is a secondary. Here we have a secondary, and a primary. And then over here we have a tertiary, secondary, and that is a primary. So looking at these, which one do we think is going to be the worst?
Would it be the second one?
So this one is going to be the worst one. And then which one do we think is the second worst?
For number 2, why is that third carbon secondary? Why isn't it primary? For the second
number, this is supposed to be.
That's supposed to be, okay, just making sure.
My bad. But there are 2 tertiaries on there, so it's kind of just like throwing the whole deal off.
Okay.
Okay.
Thank you.
So then second worst, which one do we think that's going to be?
What is the fourth one?
Yep, so this is the second worst. And now here's some more information. Bromine is larger than Cl, which means that it has a better rate. So then which one do we think is going to be the best?
The third one?
The first
Bromine is
First one.
larger. Yeah, I'm getting a lot of votes for the first one. So this one is going to be the best. And this one is going to be the second best. You guys know when we were looking at the Ken Ingold pre-log system and we were looking at the highest priority in order to determine like R and S configurations, and if we had something like OH compared to like CH3, then this one would have higher priority. It's kind of a similar concept here when we're looking at increasing rates. They all have we saw that they all have primary ones there. And the second thing that we go to look at is going to be either secondary or tertiary. So we just go to the next carbon. So then our final answer here would be 2, 4, 3, 1. Cool.
Yep.
Okay, I'm gonna go ahead and share my screen here and show you guys this question. And this is what I mean when I say that he can ask an electrostatic map question. This is just me sketching it out, so just bear with me. But over here it says, consider the following grayscale electrostatic potential map. Which electron is the most electron core? And then this would be red. Ideally, I do think our exams used to be in black and white. So, a bit of a disadvantage for us. But yeah, the answer here would just be 3 because there isn't as much like redness around it. Cool. I say cool for the next 2 weeks. I'm probably gonna have to fling myself off of a building because I've said the word cool so many times. It's just so cool. Am I right? Oh my gosh. Okay, are you guys ready for some more questions?
Yes.
Great. Okay. This is R and S stuff. Okay, that's constitutional isomer stuff. Oh, this is such a fun one. We're going to do classify each of the following. So let's say that we have something like, was this their last exam stuff? Oh, you know what? What is this from? Have you guys learned this before? Learned this yet?
Wait.
I think this is chapter 8, actually.
I mean, what are you
Wait,
trying
what are
to?
what are we looking
I
at?
don't understand.
Okay, yeah, this is an addition reaction.
We haven't done those yet.
Yeah.
When I had the class, it was really weird because chapter, like, I think it was like chapter 6 for us, was just the basics of substitution, elimination, and addition reactions, kind of just like telling us what they are and how they work. And then the next chapters after that, we had Sn1, Sn2, E1, E2, and then like addition reactions as a separate chapter. And then right before Sn1, I think we had like nomenclature of alkenes. So it was a little bit weird that the way your book is set up, but I think it will help you guys in the long run, hopefully. But this is one that I definitely know you guys will know. So what is this?
That's a
Substitution.
substitution.
This is just a substitution reaction. Substitution. Okay, cool. Next question. You guys all better know how to do this. Rank from most to least reactive in an Sn1 reaction. 1, we have this. Oh my gosh. 2, we have this. 3, we have this. And 4, I feel like I'm here complaining to you guys about how much I hate Roman numerals, but I really just cannot stop using them. 3, 4, we have this one. So what are we going to look at? What carbon?
We're going to look at the carbon surrounding, like the B position ones.
Yep, exactly. So the one coming right off of. So this is going to be secondary, this is primary, this is secondary, and then this is tertiary. And how do Sn1 reactions like to react?
Tertiary.
Tertiary, and then like secondary and stuff.
Tertiary, and then secondary, and then primary. So looking at this one, which one is going to be the most reactive?
4.
4, and then?
Would it be the bromine?
Iodine is larger than bromine. Or no, bromine is larger than iodine. Good.
No.
Yeah, right. Iodine's larger.
Iodine's larger.
Okay, iodine is larger and more reactive. So then what do we think is next?
1.
1, and then?
2.
Yeah, and then 3, because this is a primary and that's a secondary. Yep, 4, 1, 3, 2, perfect. Okay, does that make sense to everybody? Awesome. So then this is going to be provide the starting material. In the reaction, I feel kind of bad. We haven't even started elimination reactions yet. Maybe I'll stay a little extra, but what is her name? Brittany has hers, so I really don't want to take into her time. What I'm probably going to end up doing is just stopping right at 5, so you guys can hop over there and ask her all of your elimination questions. So what do we think is going to, what kind of reaction does this look like? NaSH?
Substitution.
Substitution, specifically Sn1 or Sn2?
Sn2.
Sn2.
Yep, Sn2, because we have, is this polar protic or polar aprotic?
Would that be aprotic?
Oh, I thought protic has hydrogen.
Well, the nucleophile is a strong nucleophile, but does it mention anything about the solvent?
Yeah, so this is going to be a strong nucleophile because oxygen has like the same reactivity as sulfur because it's kind of like just below it in the table. So what do we think this is going to look like? We're going to keep our ring structure. Everything like this is going to stay the same, and then that's going to be the same. So what do we think is going to be on that last bit over there? In substitution reactions, we're replacing the nucleophile with what? Or the nucleophile replaces what?
Halide.
A halogen. And our halogen specifically would be iodine, bromine, or chlorine, not fluorine.
So yeah, I had a question about this because with the like these, well, you can consider this synthesis. Can't you kind of just choose which one out of the 3? Like he wouldn't ever give us a scenario where it's like iodine, bromine, chlorine. Like he wouldn't do that.
Yeah, he wouldn't do that.
Yeah, that makes sense. Because in the book they were just like you can kind of choose out of those 3 these type of questions. Okay,
Exactly. Yeah. This one is going to be draw the products of the following reaction, and this is going to be like this, and then we have chlorine.
Wait, I'm sorry. So for the first one, was that Sn1 or Sn2?
Sn2.
It was Sn. Okay, thank you.
Yeah, this would be Sn2. And another way that we could determine how it would, what it would be, what kind of, this is going to be primary, and we know that which one reacts with primary.
Sn2.
Yep, Sn2. So then over here we have these as our, so it's actually CH3OH is how it was written out, but I like to draw it out completely. So what kind of solvent is this? Is this going to be polar protic or polar aprotic?
We would have a polar protic.
Polar protic. This is 2 degrees, so it's not really helpful for us in any way because that can go both ways. But that protic solvent is really telling us and giving us the hint that this is going to be Sn2. And then our final product is,
Sn1.
I
was about to say.
My bad. I had that secondary in there, so I was like, it's on my mind. Anyways, so then for this one, fun fact, we get 2 products out of this. Who wants to tell me why we get 2 products?
Is it because when you have the intermediate like carbocation, you can hit it from the back or the front?
Yep, exactly. So we know that Sn1 happens in 2 steps. So the first step that we're going to have here is that we're going to have chlorine leave. And then once our chlorine leaves, we're left with this carbocation. And therefore, in this, on this carbon, we don't have a front and a back. It's not, what is tertiary? It's 4, what is 4 in like?
Quaternary?
Quaternary, yeah, it's not quaternary. So it's going to be trigonoplanar, which means that you're able to go from the front or the back. So you can do a front side attack, or you can also do a back side. That's so cute, it looks like a heart. Or you can do a back side attack with this OH like this. Well, it would look like this, OH. Perfect. So then we're left with 2 products. So this is a racemic mixture. And actually, we technically have the hydrogen like this, but what would happen is that our chlorine from earlier would come in, save the day, and give these electrons to that.
Wait, what's happening with the hydroxide after the leaving group? Like, that's a nucleophilic attack, but I'm confused with the drawing.
What is happening to the hydroxide?
Yeah, is that a nucleophilic attack? Or were you explaining like?
Yeah, the oxygen is going to be the nucleophile. So over here, let me erase this because I feel like this is like a messy picture of it. So we have an oxygen like this, and then this is going to come and attack our carbocation. Right. And then we're given this structure that looks like this. I'm going to put them both on a wedge for right now. And then we have O, and then we also have the hydrogen. And there's a plus sign on that oxygen. And so the oxygen is like, I just went through this entire reaction. I just want to be happy. Hydrogen, I need you to leave. I want a fresh start. And then the chlorine is like, you know what? I got kicked off of this molecule too. So let's go and live our lives together. And that is how we get our products.
quick question though. Sorry for the background noise again. But like for this reaction, because that CH3OH is also a weak base, theoretically, can you also have an E1 reaction? And like the only way you would know it's not both is if like they had heat or something.
So when I went through, when I actually like had this question, it we hadn't learned E1 reactions yet at all. So for this one, I didn't put the elimination product, but since this is what is that, a weak base?
Yeah, it's also a weak base, so it's gonna also have like an E1 product.
So it could also have an E1 product. So I think that that would look like this, if I'm not mistaken. And then I guess this would also be another product of it. Cool. Awesome. So let's say that, okay, so yeah, Sn1, the rate of this reaction would be K this, with our original chlorine structure. And then let's say that we were to switch the, let's say that we're changing the substrate. So substrate becomes CH3ONA and acetone. So now we have this. CH3ONA, which looks like this. I personally, whenever I have a sodium like that, I like to write it separately, since they really would like dissociate just in nature like that. And our product is going to be this. And are we going to have it on a wedge or a dash?
You're gonna have it on the dash because it's inversion of configuration.
Yeah, and how do you know that it's inversion? Because what kind of reaction is this?
It's an Sn2, so you gotta hit it from the back.
Yep, we have a product, and then this is Sn2. Okay. Yep, and then the mechanism would pretty much just be this. Super easy. Okay, so we have 12 minutes.
So wouldn't that be it'd be a strong nucleophile but a weak base, right? I don't know if that's right, but yeah.
Who wants to confirm or deny that information? Because I don't know that off the top of my head.
Strong.
Yeah, that's a strong nucleophile as well as a strong base.
Okay, so we have a strong nucleophile, strong base.
So do you just recommend that we memorize these? Because there's a lot.
Unfortunately, I do just recommend that you memorize it.
But there are like some tricks. Like I know with the halides, like I know that they're gonna be really good nucleophiles outside of like fluorine, but they're all terrible bases. Like, and like I know that's what's it called? Oxygen is, if it's negative, it's always gonna be good. It's like small things. You can't like memorize every single structure. I feel like that would be like too much. But if you like recognize like patterns, it gets like really easy. So.
I feel like Dr. Downey knows how much information is on this, and I feel like he is going to keep the questions like how I've had them. So with this reaction here, I could tell right off the bat that this would be Sn2 just by the fact that I have an aprotic solvent. I wouldn't worry too much about saying like, oh, is this also, well, I guess for E1 and E2, you would also have to know that. Just memorize the strong bases and weak bases. I think if you're going to memorize anything, just know that. And then for aprotic and protic, just know that protic has a hydrogen and aprotic does not. I do have like a couple of E1 reactions I want to go over with you guys, just because I've mentioned them, and so I want to show you guys I'm not actually just a liar who's like, these are questions that Dr. Dowdy could ask. So yeah, let's do these last two questions, and then hopefully we'll have like a couple minutes to do any other ones. So let's do, what is the major product of the following reaction? So let's say that we have this, and then we have a bromine over here, and that. And then our reagent is this, KOCCH3, also known as
A bulky.
Tert butoxide.
tert butoxide. Yep, which is a bulky base. So our options here are going to be A, 2,3-dimethyl hex 1-ene. B, Z, 2,3-dimethyl hex 3-ene. C, 2,3-dimethyl hex 2-ene. Or D, 2-isopropyl pent 1-ene. So I think that the best thing to do is actually go through the reaction and then just match it up to one of those. So we have this, and this is our alpha carbon. This is a beta carbon. This is a beta carbon, and this is a beta carbon, which means that these are all the places where it could react. But we know that we're working with a bulky base. So if we were to just look at all of the products that could be formed, just with any sort of base in general, this could be a product. If we're working with this one, this could be a product. If we're working with this one, and this could be a product if we're working with this beta carbon. But tert butoxide will do elimination reactions, and then in an E2, product is the least substituted double bond. So let me write that out. For tert butoxide, product is least substituted double bond, which is this one right here. So if we were to go in, and obviously you would have to do this during your exam to figure out what answer matches up with it. But I have this done for you guys already, so don't worry. Do not fret. And then this is our last answer. And it's pretty annoying the way that this one is drawn, but this one does actually match up with it. So we have this. But if we were to flip it around, then you can see this is going to be like, if we have like pent 1-ene, so this is 1, 2, 3, 4, 5, and then this is our isopropyl. Does that make sense? You guys haven't said anything, so I'm worried now. Are you guys okay?
That makes sense.
Oh my gosh, I was like, am I muted or something? Like nobody. Okay, last question. let's do, yeah, so the answer here is B. What carbocation would likely not undergo, which carbocation would likely not undergo rearrangement? And I'm doing this one with you guys because when I saw this question, I was like, what in the world? And I cried after I got my results back. So this is 2, this is 3. Here I go again with the Roman numerals. So yeah, looking at 1, let's look at 1. And we have this as our original. We can have this as a product. This is our alpha. And then these are the surrounding hydrogens over here. So then from that, we can get this, which is a primary. Oh, I guess, okay, so this is secondary. This would be a primary. Or we would have this if it went the other way, making this a tertiary substituted. So this one would definitely happen because you're going from secondary to tertiary. 2, we have this, and we have a secondary. From this, we can do a methyl shift. Since there's no hydrogens over here, yeah, there are hydrogens over here, but something that we can do is a methyl shift, giving us this.
Where did you get the double bond from for the first one? Like, it just seems like it just came out of nowhere.
Oh, so let's say that we have some sort of like base. It would come and grab, this is the hydrogen there. It would grab this, let me do it in a different color, grab this hydrogen, and then this would move towards our carbocation that we have right here. So this is just like the way that an elimination reaction works. So let me.
Oh, so is this problem based on if there was like an elimination or substitution type of, okay.
Yeah, exactly. But it's not actually it like in, it's it like in theory, but you're still having to solve for things. Or like another way that this could happen for this specific one is that we have a hydrogen here. So it's just a way for it to become more simplified. If that's like, is it kind of making sense the way that I'm explaining it? Now that I'm looking at it, that isn't actually it undergoing rearrangement. That is it becoming negative. So, but let's just keep doing it this way. And hopefully it will make sense, hopefully. So yeah, over here, we're left with a tertiary. Then this is 3. And we have, to begin with, a tertiary. There are a bunch of different hydrogens here. And then moving it would look like this. This or this. If we were to just do a carbocation rearrangement, then like forgetting about the double bond or what the products would look like at all. It would be here, which is primary. It could be here, which again is primary, or it can be here, which is secondary. So we're going from either tertiary to primary or tertiary to secondary. So do we think that one would undergo rearrangement? Yeah, that one would not undergo rearrangement, but let's just do the last one for good measure. Figure out all of our beta carbons. We would have this, or we would have this. And this one can either go to primary, but it can also go to tertiary. So this one would undergo rearrangement. So the answer is 3. Okay, so that is going to be it, unfortunately. Hopefully that helped a little bit. What did you guys think about that? I'm going to stop the recording.
Thank you.